Let us now get into the stress strain diagram. So far, we have discussed stresses and strains. Stresses were the force per unit area, or in other words, the unit strength of a material. And the strains were related to deformations. The stress strain diagram helps us connect the stresses with strains. It helps us define something which is called strength of a material. The strength of a material depends on the ability of the material to sustain a load without any significant deformation or failure. In structures or structure mechanics, we would always want to have materials that can take maximum load and give us the least deformation. So that function is determined by the stress strain diagram. The property that is inherent in the material, which are the stresses to strains, must be determined by experiment. One of the most important experiments that is performed in this regard is the tension or compression test. We use something which is called universal testing machine to perform these type of tests. So we have some platens in the case of compression test, and we place a test specimen between the platens, and then this machine is connected to data receiving system or a data logger. We can automate the applied load and the deformation produced within the specimen. In order to read the strains, we use something which is called electrical resistance strain gauge, shown over here. The operation of this gauge is based on the change in electrical resistance of a very thin wires, which are shown, or pieces of metal foil under strain. The gauge is attached to the specimen along its length, and the extension or the compression of the element changes the electrical conductivity within this circuit, and correspondingly we receive data in our data logger. In the case of a tension test, normally we take the specimen, mark 2 points, get our initial length, and then after that we attach a strain gauge to the specimen. The strain gauge is attached firmly so that it becomes part of the specimen, and then we put it in the testing machine. The tension specimen is gripped between the jaws of testing machine. So instead of platens, we expose the jaws of the machine and place the element. So, and the jaws firmly hold the specimen. After this, the data is plotted on a graph with the ordinate representing the load and abscissa representing the elongation. Once we draw the load and elongation graph, then that is converted into the stress and strain graph by normalizing the effect of the load and elongation. The main idea of the stress strain graph is that it distinguishes one material from another. One question might arise in mind that why are we not considering load and elongation? Why do we have to resort to stress strain diagrams? So the answer will be given as follows. Imagine we have got two springs which are of the same material. One is a very thin spring, such as the one used in our ballpoints, and another one is a stiffer spring, the one used in car axles. Both are of same material, but both will show different deformation under the same load. So if we draw F is equal to Kx diagram, or load is equal to K times extension diagram, the thinner one will show less stiffness as compared to the thicker one. Thus, in order to convert the F is equal to Kx, this thought experiment clearly shows that the force is equal to stiffness time extension curves can be different for the same material. Therefore, we have to normalize the forces and the extensions or elongation within this equation. It is because of this reason that we convert the force elongation curves to stress strain curves. So if we divide both sides of this equation with area of the cross section and length, and then reorganize the variables, we get stress is equal to E times strain. Stress is equal to E times strain enable us to compare different materials with each other based on the stresses and strains. Thus, the dependency of the load and elongation of particular material has been normalized. Now let us look into the stress strain curves. Stress strain curve of different materials are different. Like for example, what we can see is the stress strain curve of three different type of steels. One is a mild steel, another one is a cold worked steel, and a hot rolled steel. Mostly the steel behavior is shown in this figure. We have got the initial portion of the curve, which is straight line, and that is called elastic region. The elastic region has a boundary at the proportional limit. In the elastic region, the equation stress is equal to E times strain is applicable. Beyond the proportional limit, the line starts to curve out, and sometime it gives us a blob as shown over here in the case of high carbon steel. Then the curve becomes flat. This region where the curve is flat is called yielding region. After that, we have a strain hardening and the necking region. The stress strain curve of steel can be better understood by taking this model or a sample of its molecules. Imagine we have got a steel sample and the molecules within the steel are arranged regularly in form of balls. So they all are contacting with each other. When we apply the load on the sample, these balls start rolling against one another. If we are below our proportional limit, then if the load is removed, the balls will rearrange themselves in the same position as before the application of the load. However, if we cross the proportional limit, or in other words, we apply load which is beyond the proportional limit, then yielding will start. The balls will start sliding against one another. So for a particular constant load, we will have an increase in deformation, as we can see in the yielding portion of the curve. This behavior will continue until a point that these molecules will get locked again and start taking the load. In the yielding region, we say that the material has become plastic because it starts flowing like plastic. After the yield point, we have got another region which is called strain hardening region. In this region, the molecules again develop some contact stresses among themselves and start taking the load. However, it is clear that the slope of the line in elastic region is higher than the slope of the line in the strain hardening region. That clearly tells us that the material has been damaged. If we remove the load, we will never come back to the original position. Or if the load is removed, the molecules will never come back to their original locations. In the strain hardening region, if we keep on increasing the load, a point will come that we reach to the maximum load. The stress which is caused by the maximum load is called ultimate stress. After that, we have extension of material and we get something called narrowing or necking of the specimen. If the area of the necking region is reduced significantly, the stress is dramatically increased over there. And as a result, fracture occurs. The stress starts reducing and the material completely severs. In the case of necking, the material stretches very rapidly and simultaneously narrows down. Thus, the rupture load is actually distributed over a smaller area. If the rupture area is measured after the failure occurs and divided into rupture load, the result is a true value of actual failure stress, although this is considered considerably higher than the ultimate strength. Nevertheless, we don't consider the rupture stress, we consider the ultimate stress as the maximum stress. some of the materials don't have well-defined yielding point. In a case of mild steel bars and hot rolled bars, we have well-defined yield points. So we have the lower yield point and we have got the upper yield point. However, in the case of cold work yield bars, the yield point is not defined. In that case, yield strength is determined by the so-called offset method. This method consists of drawing a line parallel to the initial tangent of the stress strain curve. This line is started at an arbitrary offset strain, which is 0.2% or 0.002 meter by meter or inch by inch. The intersection of this line with the stress strain curve is called yield strength. So in this figure, we don't have a well-defined yield point. Therefore, we draw a line which is parallel to the initial slope of the line, and that is at a distance 0.2%. Wherever this line hits the curve, that becomes our yield stress. This sort of behavior is common in cold worked high yield bars where the yields is not well defined. This method can be used in the case of concrete also. These are different strength of concretes and we don't have a well defined yield point. This table tells us the yield strength of different materials such as mild steel has got tensile yield strength of 165 megapascals, compression yield stress of 155. High tensile has got 230 tensile and 215 megapascal compression stress. Concrete can have compressive stress between 20 to 40, even up to 50 megapascal compressive stress has also been achieved. These are very approximate values and we can have a structure steel having a strength of 500. So in the case of steel, as you can see, the yield strength of hot rolled bars is 400. We can have mild steel bars which are up to 250 or 300 megapascals. In case of concrete, we can have different ultimate strengths. Now let us see modulus of elasticities of different materials. Steel modulus of elasticity is 210 into 10 raised to power 3 megapascals. Concrete, on the other hand, is approximately 14 exponent 3 megapascals. So steel is almost 15 times stiffer than concrete. Let us now look into this simple problem where we are given stress strain curve and this is of a steel alloy. We are asked to find out the modulus of elasticity and the yield strength based on 0.2% offset. We also have to identify the ultimate stress and the fracture stress. In this figure, we don't have any well-defined yield point. So obviously we have to use the 0.2% offset rule for finding out the yield point. The modulus of elasticity is stress is equal to E times strain, but the modulus of elasticity can be determined from the initial point of this curve. This second curve is actually a zoomed in version of the same curve. So we have tried to zoom in on this region which covers the proportional limit and the yield point so that we can easily find out the modulus of elasticity and also the yield point. We can see that the proportional limit is at approximately 50 ksi. At this point, the strain is 0.0016. Thus, we can divide 50 by 0.0016 and get our modulus of elasticity. After that, we have to determine the yield strength. So we can apply 0.2% yield point rule. We already know now the slope of this line, OA. We draw another parallel line which is at 0.2% offset from point O. Wherever this line touches the curve, that is our yield point. From this, we get yield of 68 ksi, as can be seen over here. The ultimate strength can be taken as 108. So if we draw a straight line, wherever it hits the stress axis, that is our ultimate stress. So ultimate stress comes out to be 108 and the fracture point, which is at C, that is approximately at 90 ksi. Let us do this another problem which will further make our concepts about stress and strain clear. So we are given an aluminium rod that has a circular cross section and is subject to an axial load of 10 kilonewton. If a portion of the stress strain diagram is shown in this figure, determine the approximate elongation of the rod when the load is applied. Take modulus of elasticity of aluminium as 70 gigapascals. So this rod is made up of two diameters. One is 15 millimeter and another is 20 millimeter. We don't know that whether the 10 kilonewton load is within the elastic region or beyond the elastic region for both of these segments. Therefore, we have to first of all convert this load into stress and check out whether that stress is in the elastic or beyond the elastic region. So in the case of BC, we can divide this 10 kilonewton by the area of cross section of BC. And similarly, AB, we can do the same thing. Please note the area of cross section of both of these segments is different. So for AB, we get 31.83 megapascals, and for BC, we get 56.59 megapascal. Now, 31.83 is in the elastic region. So stress is equal to E times strain can easily be applied. We can work out the extension of the AB region easily by using Hooke's law. The BC region has got stress equal to 56.59, which is beyond the proportional limit. So the Hooke's law is not applicable. Therefore, we'll have to make use of this stress strain curve to determine the strain. So strain in AB is using Hooke's law and we get the strain. The strain in BC is determined from the curve, which is approximately 0.045. Now from these two strains, we can determine the extension. The extension of the whole bar will be equal to the sum of the extension of each segment. And that's what has been done over here. The extension of first part, which is AB part, and that is obeying the Hooke's law. The second one is the nonlinear part, which is not obeying the Hooke's law. So these ones, the strain is multiplied by the original lengths to find out the extension. After this, we will now discuss Poisson ratio. Poisson ratio is another type of elastic deformation, which is the change in the transverse dimension due to axial compression or tension. So imagine if we have got this specimen and this is subject to axial tension. The axial tension in the longitudinal direction will result in stretching. However, in the transverse dimension, we will have squishing, as we can see that the area or geometry is getting reduced. That is shown by delta dash. This is also termed as the lateral strain. So there is a lateral strain due to the longitudinal strain of this specimen. This can be easily appreciated if we stretch a piece of rubber. The stretch of a rubber visibly gives us squishing of the transverse dimensions. This phenomena is called Poisson's effect, and in order to describe this phenomena, we make use of Poisson's ratio, which is shown by a nu, and that is equal to negative of strain in lateral direction to the strain in longitudinal direction. This is negative because if the longitudinal strain is extension, then the lateral strain will be squishing, and vice versa. The Poisson ratio is between 0 and 0.5. For concrete, the Poisson ratio is 0.2, and for steel, it can be between 0.25 to 0.32, 0.33. Now let us look into this problem where we have got a steel bar and the dimension of the steel bar is given to us. It is made up of A36 steel. The axial load 80 kilonewtons is applied to the bar. We are asked to determine the change in its length and change in the dimension of its cross section after applying the load. The material behaves elastically. So the change in the length and the change in the dimension that is required. Change in dimension means the transverse strains, and that is related to Poisson effect. We are told that the material behaves elastically, so therefore we can apply stress is equal to E time strain. We are in the elastic region, so we can easily find out the stress on this cross section, and from stress we can find out the longitudinal strain or strain in the z direction. Then for A36 steel, we know that the Poisson ratio is 0.32. As we discussed, the Poisson ratio is the negative of lateral strain by longitudinal strain. So we can find out the lateral strain by multiplying Poisson ratio with the longitudinal strain. And that is done over here. This strain is multiplied with 0.32 and we get the transverse strains. So there are two transverse strains because it has got two surfaces in two direction. One is in x direction, another one is in y direction. So both the cross sections, both the dimension of the cross sections will be reducing. The extension in the z direction is straightforward. We know that strain is change in length by original length. The change in length is found by multiplying the longitudinal strain with the original length, and that comes out to be 120. The change in the dimension of the cross section is similar to this one. Once we know the strain, we multiply them with the corresponding dimension of the cross section and we get the changes in the dimensions. Now let us look into the shear stress and strain diagrams. Shearing forces causes a shear deformation. This is similar to axial forces causing elongation or shortening. An element subjected to tension undergo an increase in length. An element subjected to shear wouldn't go increase in length, but it undergoes a change in the shape. So initially, if we have a square section, it will be changed into a parallelogram section. This action may be visualized for the present as equivalent to infinitesimal sliding. The sliding is shown by delta S. So the shear deformation is defined as delta S by L. Now, the relation between the shearing stress and shearing strain again assumes Hooke's law, and it can be written as tau is equal to G times gamma. G is the modulus of rigidity or shear modulus of elasticity. This is the typical tau gamma curve. G is also related to modulus of elasticity as E by 2 in bracket 1 plus mu. Different materials have got different shear stresses. If we know the modulus of elasticity, we can get the modulus of rigidity. From there, we can find out the shear deformation. Let us discuss this problem to understand how the shear deformation works. So we have a specimen of titanium alloy tested in torsion and shear stress strain diagram is shown. Determine the shear modulus G, the proportional limit and the ultimate shear stress. Also determine the maximum distance D that the top of a block of this material shown in 325B could be displaced horizontally if the material behaves elastically when acted upon by a shear force V. What is the magnitude of V necessary to cause this displacement? So we are given the stress strain diagram for this block and we are asked to determine the distance D that this block will deform into. We are also asked to find out how much shear force V is sufficient to cause this distance D so that we remain within the elastic region. Now, the first thing is to find out the modulus of rigidity. So from the sketch, from the stress strain curve, we determine at 52 KSI, we have strain of 0.008. Once modulus of rigidity is determined, then we can use the Hooke's law for shear, that is tau is equal to g gamma, and find out our gamma. Gamma is shear deformation, and gamma is measured in radians. Thus, point A is the proportional limit. So tau proportional is 52 ksi. The ultimate shear stress is 73. So this is just drawing a straight line which will hit the tau axis and we will get 73 ksi. The maximum elastic displacement can be found by taking the ratio of d by 2 to gamma. So we take the tangent of d by 2 and we find out that d is 0.016 inches. Once d is found, the shear force at, at 52 ksi, which is the proportional limit, can be found by tau is equal to v by a. So the area of the block is 3 by 4. We multiply this area by the proportional shear stress and we can easily get the shear. And that's what has been done over here.